Hello, everyone. This is part 8 of the Risk and Reliability Project, the FFIP, or Function Failure Identification and Propagation Method. Using the functional basis created during the FFDM for the control rod structure for my uh, nuclear reactor system, I have performed an FFIP analysis. This is what the basic functional model for the rods look like. Um, you can see we have a convert motor which actuates control rods which cause either an increase in absorbing slash collecting of reactivity or I guess we called it nuclear energy, or you can increase the reactivity and thus create more um, nuclear energy. That's how we thought about it. And there are several control systems in here that require input and output continuously. Now, there were several ways for this to fail. And the first few were just okay, so we have a sensor failure. What happens? It's like, okay, we have a faulty sensor flow. Okay, that just exports a faulty failed signal. Now, what happens um, if the magnetic link fails because there's an electrical power loss? Well, then you have nothing bad happens, but we no longer have the correct energy flow out of the system because the rods dropped. And then we have another same thing, but this time the control fails um, and sends a faulty signal to the magnetic link, causing a scram. We have a faulty thermal flow, flow out. Now, what happens if the motor fails because of a mechanical problem? Then we can't actuate, and either one of these two fails. And thus, if this one fails, if the absorb collect function fails, then we have a faulty thermal energy flow out. And if this fails, then we have a faulty thermal flow out as well because we had a faulty nuclear energy flow. And then this is another analysis. What if the control fails and then the convert motor fails? Same end result. We just have one more step in getting there. And then this is, okay, what if the actuate sensor fails, which causes the control to send a faulty signal to the convert motor, and then you get the same kind of failure flow as before. And now, what happens if the actuate fails because we have like a warped rod or something, so our rod gets stuck? Then you get the same kind of fail flows as before, but less steps in getting there. Okay, so what if there's a loss of coolant accident and we get a faulty nuclear energy flow in? Then our absorb slash collect fails, which doesn't necessarily fail the increased reactivity, but transmits through the flow for converting our energy, and we get a faulty thermal energy flow out. So here are a list of the cut sets, or at least the if statements that led to the cut sets for how they fail. I'm not going to go over these because it would take forever and is long. But for basically each step we say, okay, so if this fails, then we're going to export this fail flow. Then if the next function accepts the failure flow, then this thing possibly fails. And if that fails, then it's going to export, and on and on and on. And it's the same process over and over. And then we get cut sets, and we can see that we have an overall probability of failure, with the largest one, I think, actually being that first one, being from the power sensor failing, the convert power sensor failure. But the thing is that fail only sends a faulty signal to the main control center, which is probably redundantly monitored. monitored and not a huge deal. The next one is an electrical failure causes a magnetic link loss, and once again we find that electrical failures are the biggest problem that we have. Um, then followed by control failures, which is kind of interesting. I wouldn't have expected that. Well, that's what we found in analyzing FFIP on the control rods.